In this video, we're deriving the formula for the period of oscillation of a physical pendulum. So a physical pendulum is just an extended rigid body that we've hinged at one end. And then we allow the torque exerted by gravity to cause oscillations back and forth in this thing. So remember, to find the torque exerted by gravity, we're going to pretend that all the mass in the object is located at the center of mass. And then we attach the force of gravity there, and that correctly computes the torque exerted by gravity. And I'll post a link to the video where that was first derived. So we're going to want to put that weight vector into the diagram. And there it is, mg pulling straight down on the center of mass of this rigid body. And that's going to exert a counterclockwise torque in the current configuration. So that is going to cause the rigid body to move in the counterclockwise direction through the equilibrium position. But once it's over on the other side of the equilibrium position, that torque exerted by gravity becomes clockwise. And so this is why we get oscillations as this thing rocks back and forth. It's the torque changing its sign. Now to compute the torque exerted by gravity here, we need to decompose that weight vector into its radial and tangential components. And we can see the angle between the weight vector and the radial component. That's still theta. It's the same as the angle of incline at the current moment for this rigid body. And that means the tangential component, given by the opposite side there, is going to be mg sine theta. That's the part that exerts the torque, so it's the only part we really care about. And what we're going to do to try to figure out how this thing moves is use the rotational analog to Newton's second law. That's tau equals I alpha. In other words, torque is equal to moment of inertia times the angular acceleration. Now, when we start to fill in the details here, we have to be extremely careful about plus and minus signs. So I know the magnitude of the torque is going to be perpendicular component of the force, that's mg sine theta, multiplied by lever arm, which we've shown in the diagram as r center of mass. In other words, the distance from the hinge to the center of mass of the physical pendulum. But the way we've labeled things up here, it's clear that the torque is acting in the opposite direction of increasing theta. In other words, the angular acceleration that's produced here has to count as negative. So we're going to put a minus sign out in front of that guy, and this guarantees that our angular acceleration comes out as a negative number. In other words, it's in the opposite direction of increasing theta. So in the next step, I'll just isolate alpha real quick, the angular acceleration, and that's going to be negative mg r center of mass divided by I, that's the moment of inertia of this rigid body relative to the hinge, times the sine of theta. And it may not seem like it at first, but we're actually looking at a second order differential equation because alpha is the second time derivative of our angle theta. Now, unfortunately, this is a nonlinear differential equation because of that sine theta part. And this is where we have to make a small angle approximation. So we're going to assume that this angle is relatively small, and I'll actually quantify what that means in terms of how much error we're committing in a second. But for now, just take it as an assumption that the angle is relatively small. And this makes it useful to expand that sine function in a power series. So remember, the power series for sine of theta is going to be theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial and so on. You could also call this the Maclaurin series for the sine function. And I'll post a link up at the top to where this was first derived. Now, if theta is really small, then it's justifiable to do an approximation where we ignore higher powers of theta because higher powers of a very small number create even smaller numbers. So we can say that sine theta is approximately equal to theta if theta is small. In a lot of textbooks, this will normally be notated like this: if theta is much less than 1. So I want to address how accurate this approximation actually is for a real angle. So what I did was choose 15 degrees. And I compared the values of sine theta and theta. Now remember, we're talking about theta in radians here, so I had to do that conversion. And I took the sine of 15 degrees and I compared it to the radian equivalent of 15 degrees. And what I found was about a 1% difference. So we actually have a pretty accurate approximation here. And if you want it to get better, you could just choose a smaller angle like 10 degrees or 5 degrees. All right, so now we're going to rewrite this differential equation after making the small angle approximation. And we find the second time derivative of theta with respect to time is going to be negative mg r center of mass over the moment of inertia I times theta. And this is a classic differential equation for an oscillatory system where the solutions are essentially guessable. What I'm asking here is, what's the function that I differentiate twice with respect to time to get back the original function, theta in this case, with a minus sign and with some constants attached. And the answer is we get sines and cosines out of this, because when you differentiate those twice, you get back the same function with a minus sign, but we need to put a coefficient on t in order to produce mg, our center of mass, over I after two derivatives. So we can write this solution as a linear combination of a sine term and a cosine term. Alternatively, you could use a single sinusoidal function with a phase angle, but I'm going to choose the sine cosine approach here and say that theta of t is going to be a times the sine of the square root of mgr center of mass over I times t. So that term should satisfy the differential equation. Just verify it for yourself. If you differentiate twice, then each time you use the chain rule, it produces a factor of square root mgr center of mass over I. So after two derivatives, you do get this expression out in front, mgr center of mass over I, and a minus sign because the second derivative of the sine function gives you negative of the sine function. Now the cosine function behaves exactly the same way. So we have a second term in our general solution here, and it looks just like the first term. It's a cosine of the square root of mgr center of mass over I times t. So that's the general solution of the physical pendulum, but all I'm really interested in right now is finding the period of oscillation. So all I have to do is remember that the period is given by 2 pi divided by the coefficient of t. So that's going to be 2 pi times the reciprocal of this coefficient. In other words, 2 pi times the square root of I divided by mg, r center of mass. So now that we have a formula for the period of oscillation of a physical pendulum, let's apply it to a familiar rigid body. In our example here, we're asked to compute the period of oscillation of a thin rod with mass big M and length big L, where we've hinged it exactly about one of its ends. And of course, we're told to assume the oscillations are small because our formula isn't valid if the oscillations aren't small. So we already determined the period of oscillation of a rigid body is given by 2 pi square root of moment of inertia divided by mg times r center of mass. So we have to recall first that the moment of inertia of a thin rod about one end is given by 1/3 ml squared. And I'll post a link to the video where that was derived by using physical integration. And then the r center of mass in this case, well, the hinge is at one end of the rod and the center of mass is at the middle because it's just a thin uniform rod. So the distance between those is just L over 2. So we can plug in and find our period. And there's our moment of inertia, 1/3 ml squared. And then in the denominator, the mass was big M, and there's our G. And our R center of mass is L over 2. So the M's are going to cancel out of this, and 1 L cancels out of this. And we arrive at a period of oscillation of 2 pi square root 2/3 L over G. Now I think it's useful to compare this to the simple pendulum formula. Recall for a simple pendulum that the period of oscillation was 2 pi times the square root of L over G. In other words, that factor of 2/3 wasn't there. So this means the period of oscillation for our thin rod is actually going to be faster than for a physical pendulum with the same mass and total length. So I'll say compare this to the period of a simple pendulum. So I wrote that as TSP, which was 2 pi root L over G. And if we pull that factor of 2/3 out and just get a decimal approximation here, the way it turns out is that the period for our thin rod is approximately 82% of the period for a comparable simple pendulum. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.